This is the Chapter 4 exam review. Problem 1, approximate the following number using a calculator, 7 to the negative 1.7. And it is asking me to round this to 3 decimal places as needed. All right, so I'm going to open my calculator. And I am going to raise 7 to the negative 1.7 power. So 7, I'm going to use my caret to raise that to a power, and it's the negative 1.7 power. So I get 0.0365875, etc. And they tell me to round this to 3 decimal places. So I'm going to round this 6. Since the number to the right is 5, I'm going to round that 6 up to 7. So it's going to be 0.037. Problem number 2, raise e to the negative 0.07 power. So again, I'm going to go to my calculator and do that on my calculator. All right, so on my calculator, my E button is above my natural log button. So you can see my mouse circling around there. So I'm going to go second natural log, and that's going to give me e to the power, and I'm going to raise it to the negative 0.07. And I get 0.93239381199. And it does tell me again to round this to 3 decimal places. So that's going to be 0.932. I'm rounding the 2. Since the number to the right of it is less than 5, I just truncate this. Just delete all the numbers to the right of the 2. So 0.932. All right, so we'll write that down. 0.932. All right, the next problem is a graphing problem, and you will be graphing it obviously using the graphing tool on My Lab Math. It says use transformations. Transformations actually are on your formula sheet. There's a section on your formula sheet that shows you all the transformations. Use transformations of the graph f of x equals e to the x. So when you graph this using the tool in My Lab Math, it will default to graphing f of x equals e to the x. That is the initial graph that when you open the graphing tool, pick the exponential tool, and then click anywhere in the graph, that's what it's going to graph. Again, use transformations of the graph f of x equals e to the x to graph the given function. Be sure to give the equation of the asymptote. Use the graph to determine the function's domain and range. So we're going to graph h of x equals e to the 3x plus 2. So what transformations are occurring here? So first of all, this plus 2 here, adding 2 to the function e to the x, is going to move that up 2 units. So we're going to go up 2 units. And the 3 times the x, we're taking the input x and we're multiplying it by a constant bigger than 1. That means this is a horizontal shrink. If we multiply x times a number bigger than 1, that is a horizontal shrink. So when I go into the graphing tool, I'm going to pick the exponential, just click anywhere on the graph, and it will graph e to the 3x. And then I'm going to use the graphing tool to tell it to shift that up 2 units and to shrink it horizontally by a factor of 3. So there are little input fields that you can put that in, and it will do that. Now, since I've moved it up 2 units, that's going to change the range of this function, and there's going to be a horizontal asymptote at y equals 2. We've taken that exponential function and moved it up 2. So I'm going to graph using the line tool in Pearson MyLab Math, the asymptote y equals 2. So I'm just going to write that out here so you know what I'm doing. And then I'm going to graph this thing by shrinking it. And I'm going to shrink it horizontally by a factor of 2. And I'm going to shift it vertically up 2. Okay, so it looks something, I don't know, something like this. It kind of like that. Okay, so then let's answer the rest of this question. What equation represents the asymptote? Well, I wrote that already. That is y is equal to 2. And you do need to write it as an equation. It says right there. Let's highlight that. It says type an equation. So you have to have equals in there. It's not an equation if you don't. What's the domain? Well, the domain of every exponential function in existence is the set of all numbers. We define it deliberately, so the domain is the set of all numbers. But what's the range? Well, there's an asymptote at y equals 2. So the range is going to go from 2 to infinity. And you don't include 2 in the range because the y value can never be 2. No matter what x you put in there, you're never going to get 2 for a y value. So don't include 2 in the range. All right, suppose you have $15,000 to invest. Which of the two rates would yield the larger amount in 5 years? 10% compounded monthly or 9.89% compounded continuously. And both of these formulas are on your formula sheet. So let's do the first one. Let's do 10% compounded monthly for how many years? 5 years, and we're going to do $15,000. So the formula for the first one is A equals P times 1 plus R over N to the NT. Since we're investing $15,000, P is 15,000. We're investing at a rate of 10%, so R is 10%, but we can't do a mathematical calculation using a percentage, so we divide that by 100 and we get 0.10. And we're compounding monthly, so there are 12 months in a year. So N is 12 for 5 years. So we're going to plug and chug. So the amount we have in the account is 15,000 times 1 plus 0.1 divided by 12. And we're going to raise that to the 12 times 5 power. So I'm going to go to my calculator and I'm going to do this on my calculator. All right, so I have 15,000 times, I'm going to open those parentheses, 1 plus the interest rate, which is 0.1, divided by the number of compounding periods in a year, which is 12. And I'm going to raise that to the 12 times 5 power. So I get $24,679.63. 24,679.63. All right, so let's go back to my review. So now we're going to calculate the compounding continuously. So for continuous compounding, the formula is much easier to use. It's P times E to the RT. And again, T is 5 years. But R, we're now looking at what, 9.89% compounded continuously. So we divide that by 100 and we get 0.0989. So we're going to plug that in. We're going to invest 15,000 times e to the 0.0989 times 5. So we're going to go do that calculation on our calculator. All right, so here's my calculator. So I'm going to do 15,000 times e, so second natural log, and we're raising e to the 0.0989 times 5 years. And I get $24,595.17. So let's go write that down. So I get A is $24,595.17. So which one's more? Well, it looks like this one's more. Looks like if I invest my 15,000 at 10% compounded monthly for 5 years, I'm going to make more money. So it's the 10% compounded monthly. All right. Number 5, write the equation in its equivalent logarithmic form. So I have 9 to the x is 14. The logarithm is equal to that exponent, so x is equal to the log, the base is the base that you're raising to that power. So it's log base 9 of 14. So the logarithmic equivalent to 9 to the x is 14 is log base 9 of 14. That's what the logarithm is. It is the exponent you raise 9 to get the number 14. All right, another graphing problem. We're going to graph a logarithm. Begin by graphing f of x equals the log of x. So you're going to go into your graphing tool and you're going to click the logarithmic button, and you can just scroll over each of the choices that you have in your toolbar, and it will tell you which one is which. The logarithm is the one that looks like this. All right, so what are we doing here? Use transformation. So what are we transforming? Well, we're subtracting 6 from the log of x. So that is a shift down. We're subtracting that 6 from the log, from the function. So that's a shift down 6 units. Graph and give the equation of the asymptote. We're just shifting it down. So the asymptote's still going to be the y-axis. The asymptote for a logarithmic function is the y-axis. Unless you shift it horizontally, you're not shifting the asymptote. So the asymptote's going to be x is equal to 0. So you go into your toolbar, your graphing toolbar, you graph the logarithm, and then you tell it in the toolbar to shift it down 6 units. And it looks something like this. Let's see if I can draw this. It's going to go through negatives. It's going to go right there. So it's going to do something like this. All right, so then let's fill in the rest of the problem. The asymptote is x equals 0. We haven't shifted it horizontally, so the vertical asymptote for the logarithmic function is still x equals 0. What's the domain? Well, the domain of the logarithmic function log of x is the set of positive numbers. So the domain of this thing is the set of positive numbers. But since I've shifted it down, well, I haven't done anything to it, have I? Is the domain the same? I haven't shifted it left or right, so the domain is going to remain the same. It's still going to be the set of positive numbers. And what's the range? Well, the range of the logarithmic function is the set of all real numbers. Since the logarithm is the inverse of the exponential, and the exponential function's domain is the set of all real numbers, then the range of the logarithmic function will be the set of all real numbers. All right, problem 7, find the domain. Well, this one has been shifted horizontally. So we have h of x equals the log base 7 of x minus 2. Subtracting a number from your input x is a shift to the right. If I shift to the right 2 units, then that domain up there that was 0 to infinity gets shifted to the right 2 units. So the domain gets shifted. So now it's not going to be from 0 to infinity, it's going to be from 2 to infinity. Now, the other way to look at this is the logarithm must be positive. You can't, well, the logarithm's not positive, but what you take the logarithm of, the input of the logarithm must be a positive number. Remember the basic logarithmic function, its domain is the set of positive numbers. So x minus 2, what you're taking the log of, has to be positive. It has to be bigger than 0. It has to be. So if I add 2 to both sides of that inequality, I get x is greater than 2. Well, x is greater than 2 is from 2 to infinity. All right, write the equation in exponential form, then solve. All right, so what do we have here? My base is 4. That's my base. I'm raising that to the second power. Whatever the logarithm is equal to is your exponent. So I have 4 squared is equal to what I'm taking the log of, which is x minus 1. So the exponential form is 4 squared equals x minus 1. Now let's solve that. I'm going to square the 4 and then add 1 to both sides. So x is 17. X is 17. And I can do a quick check of that. So I have the log base 4 of x minus 1. Is that equal to 2? Let's let x be 17. Log base 4 is 17. Oh, I got a boo-boo up here. My parentheses, and well, since I'm erasing, I'll make that look neater. X minus 1 is equal to 2. So the log of 17 minus 1, is that equal to 2? That's the log base 4 of 16 is 2, and that is true because the logarithm is equal to the exponent that you would raise 4 to get 16. So that is correct. All right, use the properties of logarithms to expand the logarithmic expression as much as possible. Evaluate logarithmic expressions without using a calculator if possible. So this is the log of a quotient. So the property you're going to use is the quotient property. And the logarithm of a quotient is the difference of the two logarithms. So you're going to take the log of the numerator and you're going to subtract the log of the denominator. And the natural log of e to the 7th is 7. The log of any base of b to the n is equal to n. So the natural log of e to the 7th is 7 minus the natural log of 3. And it doesn't ask for a decimal approximation, so I'm going to type that into the answer field. All right, now the next one, we're going to do the opposite of expanding. We're going to compress it. Use the properties of logarithms to condense the logarithmic expression below. Write the expression as a single logarithm whose coefficient is 1. Where possible, evaluate logarithmic expressions. Okay, so we're going to use 2 rules. We have constants outside the logarithm, so we're going to use the power rule to take those factors into the logarithm as an exponent, and then we have a difference, and we can condense the difference of 2 logarithms into a single logarithm of a quotient. So we're first going to take those factors in, so let's write this over here. We have 3 natural log x minus 6 natural log of y. So we're going to take that 3 in as a exponent. So we've got the natural log of x to the third minus. We're going to take that 6 in and make it an exponent on the y. And then we have a difference. So that's going to become a quotient. So it's going to be the natural log of the first thing, the x to the third, and we're subtracting the natural log of 6, so that goes into the denominator. Natural log of y to the 6th. I'm not sure what I said there. So it's the natural log of x to the third over y to the 6th. So the natural log, and I used parentheses. I don't know that my lab math cares, but I did use parentheses when I inputted my answer. All right. Number 11, use common logarithms or natural logarithms in a calculator to evaluate the expression. So I'm going to use the change base. I'm going to actually do it the 3 ways that we showed you in class. I'm going to use the common log, I'm going to use the natural log, and then I'm going to use the log base, which is in your math menu on your TI-84. So the change of base formula says that the log base 16 of 11 is the common log of 11 over the common log of the base. So it would be the log of 11 over the log of 16. Or you could use the natural log. It would be the natural log of 11 over the natural log of 16. Both of those will work just fine and dandy. Or you could use in your math menu on your TI-84, you could go math, go down to A, and that would be log base. So that will find the log of any base for you. So let's go do it all 3 ways. I don't care how you do it, whatever you want to use. I mean, you do have a log base available to you, but it's the change of base formula is so easy to use that we could use it too. So let me clear out my screen here. So I'm going to take the log, the common log of 11. Be sure you close those parentheses and divide that by the log of the base, which was 16. So the common log base 10 of 16. Close those parentheses. And I get 0.8648579. So then I'm going to show you that it get the same answer if I use the natural log. So the natural log of 11 divided by, oops, didn't I close my parentheses? I didn't. We're going to do that. Divided by the natural log of 16. If you don't close your parentheses, you're going to get the wrong answer. It's just the way it is. Okay, or I could go to my math menu over here on the left, and I could scroll down till I find A. That's log base, and it's the log base 16. Use my arrow to get it over inside the parentheses, 11. So 0.865, how many decimal places? 4 decimal places. So 0.864, I'm going to be rounding off the 8. Since the next number to the right of the 8 is 5, I'm going to round that 8 up to 9. So I'm going to type in 0.8649. All right, solve the following exponential equation by expressing each side of the power as a power of the same base, then equating exponents. So I have 2 to the 3 minus x equals 1 over 8. And I happen to know, because Professor Castle yelled at me in class, that 8 is 2 cubed. So this is 2 to the 3 minus x equal to 1 over 2 cubed. I happen to know from the laws of exponents, if I have a base raised to an exponent in the denominator of a fraction, I can move that to the numerator by changing the sign of the exponent. That's the reciprocal rule of exponents. So that's going to be 2 to the 3 minus x is equal to 2 to the minus 3. When I move that 2 to the third to the numerator, I change the sign of the exponent. Now the bases are the same. I equate the exponents. Write that correctly. So I have 3 minus x is equal to negative 3. I'm going to subtract 3 from both sides. And I get negative x. That negative in front of that x didn't go anywhere. Negative 3 plus negative 3 is negative 6. And then divide both sides by negative 1. And I get x is positive 6. I am going to check that. So I have 2 to the 3 minus 6 is 2 to the minus 3. From the laws of exponents, that's 1 over 2 to the third, which is 1/8. So the solution is 6. All right, the next problem. Your rules for solving exponential equations using taking the log of both sides says that you have to isolate the x. Oh, my highlighter's not helping any me at all. I have to isolate the exponentials when I'm trying to say. And I was trying to highlight the 7 to tell you that I have to get rid of the 7. I can't solve this exponential without getting rid of that 7. I have to. So the easiest way to get rid of the 7 is to divide both sides by 7. And as I said in class, all of these problems that I have ever encountered in this book, the number on the right will be divisible by whatever that coefficient is. And 707 is divisible by 7. So we're going to divide both sides by 7. 7 over 7 cancels. I get e to the 2x is equal to 101. 707 divided by 7 is 101. Then we're going to take the log of both sides. We're going to take the natural log specifically. And then the natural log of e to the 2x is 2x. The natural log of e to the anything is whatever that exponent is. That's the natural log of 101. And then we divide both sides by 2 to isolate the x. So the solution set expressed in terms of logarithms is the natural log of 101, the whole thing divided by 2. Now I need to go get a decimal approximation. How many decimals do they want me to approximate? 2 decimal places. So I'm going to go to my calculator. And I'm going to take the natural log of 101. Close those parentheses. And I'm going to divide that by 2. And I get 2.31. If I round off to 2 decimal places, I'm going to round the 0 off. The number to the right of that 0 is bigger than 5. 5 or bigger. And I'm going to round that 0 up to 1. So it's going to be 2.31. All right, problem 14. Solve the logarithmic equation. Be sure to reject, and I'm going to highlight this. Be sure to reject any value of x that is not in the domain of the original logarithmic function. Okay, what is the domain? Let's just talk about that just for a second. The first expression I have on the left-hand side of this equation is the log base 9 of x. So that's just a standard logarithm whose domain has to be the set of positive numbers. You cannot put a negative number in for x there. So looking at that first expression, the domain is the set of positive real numbers. Now the second one's a little trickier because I have to set 8x minus 1 greater than 0, which I can do. It's not that big of a deal. 8x minus 1 is greater than 0. Then I'd add 1 to both sides of the inequality and then divide by 8. So x has to be bigger than 1 over 8. So the intersection of those two is that x has to be greater than an 8. So if you get a solution that's less than an 8, that's not a solution to this. Now, specifically what you're looking for is, am I going to get a negative solution? And the answer is probably so. If you get a negative solution, it isn't a solution. That's an extraneous solution. That is not actually a solution to the logarithmic equation. All right, so let's solve this. The first thing I'm going to do on the left-hand side of this is combine those two logarithms. I'm going to condense the logarithm, those two logarithms. So since I'm adding two logarithms together, I can condense that by writing that as the logarithm of the product. So let's put this over here. So I have the log base 9 of x plus the log base 9 of 8x minus 1. And that is equal to 1. So I'm going to combine those. So that's going to be the log base 9 of x times 8x minus 1. So I combine the sum of two logs to the log of a product, and that's going to be equal to 1. Now I could multiply this now, or I can wait. I'm just going to multiply it here in a second, but I am going to have to write this as an exponential. So write as an exponential. So the base is 9. What I'm raising it to is what the log is equal to. So I'm raising 9 to the first power because that logarithmic expression is equal to 1. 1 is the exponent that I'm raising 9 to, and that's equal to the x times 8x minus 1. And this is going to give you a quadratic equation, which you can solve however you want to solve a quadratic equation. And I know it's going to be quadratic because I'm going to multiply an x times an 8x, which is going to give me 8x squared. So I'm going to write it down here. 9 equals 8x squared minus x. I'm distributing that x across each of those. And then I'm going to move the 9 over to the right-hand side. 8x squared minus x minus 9 is equal to 0. And I did two properties in one step. I used the reflexive property because I like to have my trinomial on the left-hand side and 0 on the right. That's just a personal preference. Now I'm going to solve this using factoring. I'm too lazy to use the quadratic formula. So I got a sneaking suspicion that it's going to be 8x and x. I know, I kind of get that inkling because I'm going to have to put a 9 in there so that I get a difference between the first and the last. That's -1. So I'm going to put a 9 there and a 1 there. And I think it's going to be minus, and I think it's going to be plus. Okay, let's FOIL that to confirm that I factored it correctly. So I multiply 8x times x, I get 8x squared, okay? Then I multiply outside, 8x times positive 1 is positive 8x, all right? Then I multiply inside, I get -9 times x, -9x. Then I add those two together. So I have 8x minus 9x gives me minus 1x. All right, that's the middle term. And then I multiply last. -9 times positive 1 is -9. So my last term in my trinomial should be -9. So I have factored that correctly. So now I'm going to set each factor equal to 0 and solve the resulting equations. So I'm going to add 9 and divide by 8. X is 9 over 8. I'm going to subtract 1. X equals -1. Nope, 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 That is not a solution. It's not a solution because I talked about earlier in this problem that if x is -1, I have a problem right there. I actually have a problem there too, honestly. Either one of those, if you try to put -1 in there, it is not going to work. You're going to get an error if you try that on your calculator. So what's the solution? Well, it's the other number, the 9/8. All right. Problem 15. Use the formula A equals P times e to the RT. This describes the accumulated value A of a sum of money P, the principal after T years, at an annual percentage rate R in decimal form, compounded continuously. Complete the table for a savings account subject to continuous compounding. So I have $7,500 that I'm investing at 8%, and I'm looking to how long is it going to take me to double my money? So if I plug this in, A would be the double or doubling 7,500. So it's going to be 15,000. Investing 7,500 at a rate of 8%, which is 0.08, divide by 100. I could probably erase that, make that neater. And I need to know how long that's going to be. So I'm going to make those substitutions. And I know I'm all over the place on this review, but that's okay. So I have 15,000. 15,000 equals 7,500. E to the 0.08 t. So I'm trying to solve for t. So I'm going to divide both sides by 7,500. And it is no coincidence, by the way, that the left-hand side is 2. We are doubling our money. Okay, and then to solve this, we can write this as a logarithm, or we can take the log of both sides, gives us the same result. So we're going to take the natural log of both sides. When I take the natural log of e to the anything, it is the anything. Divide both sides by 0.08. And that'll give me the time t in years. And it tells me to what? Round to 1 decimal places as needed. So let's go to our calculator and let's do that calculation. The natural log of 2 over 0.08. So the natural log of 2, I need to close those parentheses, divided by 0.08. So it told me to round to 1 decimal place. So I'm going to round the 6, if my mouse will work here. I'm going to round this 6 right here. So I go one number to the right, that's a 6. So I'm going to round that 6 up. So it's going to round to 8.7. Oh, I got a mistake somewhere. Where did I make my mistake? See, this is one of those cases where you go, oh, she made a mistake on purpose. No, I didn't. Let's go back to my calculator. I must have typed in something incorrectly. No, it looks good. All right, 8.7. If you know where I made my mistake, let me know. Oops, 8.7. Put it in the right field. Okay, I am going to, while you're sitting there listening, I'm going to take my calculator out and do this again. Oh, I'm good. I'm good. All right. The issue is that the problem I did earlier um, had an 8%, and the problem I did for the actual review was 11%. So that's what's confusing me ever so slightly. I'm good. It's 8.7. All right. Problem 16, after all that, is the gimme problem of the exam. You should not get this problem incorrect. I promise you, you should not get this problem incorrect. Okay, so the exponential growth model, let me explain why. The exponential growth model is A equals A sub 0 e to the kt, where k is the growth constant. A sub 0 is the amount you start with, and A is the amount you have after t years. So they give you an exponential growth model of 976.9. So that's the initial population times e to the 0.016. So that's your growth constant times t. And they ask you, and they tell you that this is the model that models population after the year 2003. So use the model to determine the population of the country in 2003. Well, that's the initial amount. If this model models after 2003, 2003 is time t equals 0. And if I raise any base to the power of 0, I get 1. So this model says the initial amount is 976.9. That is the initial population in this growth model. So whatever that coefficient is, that is your answer. So don't get this wrong, 976.9. That's a free points for you. All right, now the next one, you're going to actually have to do some calculation. So what are we doing here? Flip my page over. Complete the table shown to the right for the population growth model for a certain country. So the initial population in the year 2006 is 78.4 million. We want to know what it's going to be in the year 2043, and they do give me a growth rate of 0.0141. So again, our formula is A equals A sub 0 e to the kt. They give me the growth constant k, and they give me the initial amount. This is A sub 0. So my model is A equals 78.4 e to the 0.0141 t. That is my growth model. So I need to figure out what t is, and then it's a plug and chug. So the 78.4 is for the year 2006. We're interested in 2043. So we need to figure out how many years it's been since 2006 if we're in 2043. So we just subtract it. 2043 minus 2006 is 37. So T is 37. So let's write it down here. A equals 78.4 e to the 0.0141 times 37. So we're going to go back to our calculators. Let's go ahead and clear out all that calculation we had prior to this. And what are we doing? We're doing 78.4 times e, which is above the logarithm, second logarithm, and we're raising that to the 0.0141 times 37 years later. And we get the population after 37 years is 132.095339. And it tells me to round this to one decimal place. So I'm rounding the 0. Since the number to the right of 0 is 5 or bigger, I round the 0 up to 1. So that's going to be 132.1. All right, last but not least. An artifact originally had 16 grams of carbon, 14 present. The decay model is, so they give us the model. 16 e to the minus 0.0000121 t. And you'll notice that the problem above is a exponential growth, and k is positive. In this case, k is negative, so this is decay, exponential decay. Describes the amount of carbon-14 present after t years. Use this model to determine how many grams of carbon-14 will be present in 6,040 years, 43 years. So this is a plug and chug. So A equals 16 times e to the minus 0.0000121 times how many years? 6,043. So we're going to go put this in our calculators. So we have 16 times e to the, and we're going to need to make that negative, so use your negation key, 0.000121 times 6,043. And reading the instructions, they say to round to the nearest whole number. So we're going to round the 7. That's the first whole number that we have here. So the number to the right of that 7 is also 7 in this case. So that's 5 or bigger. So we round that 7 up to 8. So the answer to our last problem is 8. If you have any questions, please let me know.